Okay everybody, so today we're just going to look through the questions on series and parallel resistors from page 320 and 321 of the Physics Plus textbook. So question 1 just gives us a few different resistor combinations and asks us to find out the combined resistance across each of these arrangements. So we'll start off with question 1a first of all. These two resistors are presented in series. So we'll write out a formula for series resistors. Total resistance equal to R1 plus R2. There's two of them. But it could go on to 3, 4, 5 if we needed it to. So resistance 1 is 2 ohms, resistance 2 is 7 ohms. So this means the total resistance is 2 plus 7 or 9 ohms. For B, we're going to use a slightly different system. They're parallel resistors. So the formula is going to be 1 over the total resistance is equal to 1 over resistance 1 plus 1 over resistance 2. Filling in the values we have, we end up with 1 over 3 plus 1 over 9. Now it can be tempting here to decide to flip each of these fractions and then try and get RT is equal to 3 plus 9. That will not work, so do not do it. You can't just get the reciprocal of every term individually. You can only do that if you have one term on each side. So if in doubt, do not do stuff like that. So what we're going to try and do is just simplify the right hand side first of all. You can do that with your calculator if you wanted to, or you could use your knowledge of fractions. I'm going to use my knowledge of fractions, so I'm going to change 1/3 to 3/9. Then I have 3/9 plus 1/9 is equal to 1 over the total resistance. So 1 over RT is equal to 4 over 9. Now I mentioned that it is possible at this point to flip the fractions or get the reciprocal of both if you have just one term on each side. So I'm going to do that now. If you're not comfortable doing that, you can also just do it out the long way. So cross multiplying 4 RT is equal to 9, and then RT will be equal to 9 divided by 4. So this gives us RT is equal to 9 divided by 4. When we calculate this out as a decimal, we get 2.25 ohms. Now we move on to part C. So for part C, we've got 2 parallel branches, but one of them is made up of more than one resistor. So what I'm going to do is I'm going to break this branch off, and we can call that RS for the series section of the resistors. And we can say that that will be equal to the sum of these two individual ones. Then later on we can get the total resistance of this piece of circuitry by treating this RS and the 9 ohm resistor as being just two resistors in parallel. So to get the resistance of the series part, first of all, it's going to be R1 plus R2, should be 3 plus 6 or 9 ohms. I'm making sure to write this down underneath so it's clear to whoever's marking my work what I mean by RS. Now to get the total resistance, I'm going to use the parallel circuit formula because RS and the 9 ohm resistor are in parallel now. So I'm going to have 1 over RS plus 1 over 9. And maybe even take a step back from there. I'll say 1 over resistance 1 plus 1 over resistance 2. Just to make it even more obvious, I guess, for the person marking it. So 1 over RT, I can now fill in 9 ohms for one of them, and it's actually going to be 9 ohms for the other one as well. So this could be RS, and the other one is the 9 ohm resistor. That gives me 1 over RT is equal to 2/9. So RT itself, remember we can flip them if we have just one fraction on each side, get the reciprocal of each. So we get 2 over 9, or you can do it in your calculator. It becomes 9 over 2. So 4.5 ohms is the total resistance of that arrangement of 3 resistors. We're going to do something pretty similar then for the next bit. We've got for D 2 resistors that act on a block, and then they're connected in series to the other 300 ohm resistor. So we'll treat this as one block, find out its resistance. Let's call that OR parallel. And then at that point, OR parallel is in series with the 300 ohm resistor. So we can get the combined resistance by adding them like for any other series components. So for the parallel components, say that 1 over OR parallel is equal to 1 over 300 plus 1 over 300. You can write out your formulas obviously, but I'm not doing it at this point because I've done it a few times. I don't want the video to go on longer than necessary for you. So I get 1 over OR parallel is equal to 2 300ths. Again, use your calculator if you're not sure about the adding fractions. So now, because I have one term on each side, I couldn't do it before. I can get the reciprocal of each. So I get OR parallel over 1 is equal to 300 over 2. So the parallel resistance is 150 ohms. To get the total parallel or total resistance for D now, we're going to add the parallel component plus the series component's resistances. Because they are now in series, we can say that the total resistance is equal to OR1 plus OR2. So OR1 we can say is 150 ohms, OR2 we're told is 300 ohms. So the total resistance is 450 ohms. Now we're finally on to part E. So what we're going to do is treat each of those parallel components as a block, and those blocks then are in series. So we'll find the resistance of each parallel block, and the resistances actually will be the same for each of these parallel blocks, and because they each have a 400 ohm and a 600 ohm resistor. So to find the resistance of one parallel block, it'll be 1 over OR parallel is equal to 1 over OR1 plus 1 over OR2. And we fill in the values for a 400 ohm resistor and a 600 ohm resistor. I'm feeling too lazy to do that in my head, so I'll do that one in a calculator. And it's telling me that 1 over OR parallel is equal to 1 over 240. So this is here from earlier on. What I'm going to do then is I'm going to get the reciprocal of each side, because I only have one term on each side, one fraction. So that gives me 240 ohms for each parallel branch, right? So now I just have to remember that to get the total resistance, I'm going to add 2 of those parallel branches together. So they act as a series circuit. So the total resistance is the sum of the individual resistances. So total resistance is going to be 240 plus 240, because each of those has the same resistance. So if we find the sum of those, and that's going to give us 480 ohms. For question 2, we're told that we have 4 2 ohm resistors. We're asked to draw diagrams to set them up so that they have a combined resistance of 8 ohms, 0.5 ohms, 2 ohms, and 5 ohms. So the first one, 8 ohms, is probably the least tricky. So to get 8 ohms, we would just set them up in series. So we'd sum the resistances together, and 2 plus 2 plus 2 plus 2 will give us 8 ohms. If you want to be super sure of your marks, I'd label each of those as 2 ohms. The next one we're asked to get is 0.5 ohms. That is the smallest resistance we can get from them, so I'm fairly sure that the best way of doing that would be to put them all in series. So or all in parallel rather. So 1, 2, 3, 4. So we'll just check this out now by using the parallel resistance formula. So this gives us 1 over total resistance is 4 halves. So then the total resistance will be 2 over 4 or 0.5 ohms here. Again, to be sure of a mark for the diagram, I'd probably write in the individual resistances of each. Okay, so for the next arrangement, what I'm going to do is look at setting up 2 resistors in parallel and see where that gets me. I'm trying to get to 2 ohms. So this is for part C. And so if I set up 2 in parallel, what I get is 1 over RT is equal to 1 over 2 plus 1 over 2. So 1 over RT is equal to 2 over 2 or 1. So the total resistance for that is 1 ohm. So if I just combine 2 of them together, I'll be able to get 2 ohms like they want me to get for C. So the total resistance here will be then 1 ohm plus 1 ohm for each of those parallel sections or series sections. So that gives me 2 ohms. So I'm going to use the information I gathered there about setting up 2 of them in parallel, and I'm going to use that then for part D, because for part D they want me to get an arrangement that will give a resistance of 5 ohms. So we're working towards 5 ohms. We know that a section like this will give us a resistance of 1 ohm. So we need to increase that by 4 more ohms. So to do that, if we add 1 more resistor in series, that will give us another 2 ohms. So we're up to 3 ohms altogether, and then another one give us another 2 ohms, so we're up to 5 ohms altogether. So that will be the arrangement there for D. So question 3 is actually a pretty hard question, or it can, I guess, be a brute force one depending on what way you want to do it. So let's approach it from both ways, and we can do a brute force and then kind of come up with maybe a little bit more of a clever way of doing it then based off that. So if we have one resistor and it's a 2 ohm resistor, then the resistance will be 1 over 2. So the total resistance will be 2, right? 2 ohms. If we decide to go with 2 resistors, RT will be 1 over 2 plus 1 over 2. So 1 over RT is going to be equal to 2 over 2 over 1. So total resistance is 1 ohm. If we do it for 3 resistors, then 1 over RT is equal to half plus a half plus a half. We could say that RT is equal to 3 halves, and then RT itself is 2/3. And we can keep doing this until we get down to whatever value it is that we're looking for. In this case, they want us to get to 0.25 ohms. And it's fine if you wanted to use that as a brute force method. I wouldn't spend very long in an exam if they didn't give many marks for it, but I think it would be a higher mark question in an exam. The alternate way, which is probably a little bit more time efficient, is to realize that if there's one resistor, then it's going to be 1 times a half over here. If there's 2 resistors, then it's going to be 2 times a half over here. 2 lots of a half plus a half. If there's 3 resistors, then it's going to be 3 times a half. So we know that whatever amount of resistors there are, it's going to be multiplied by a half. We can apply this then to the parallel resistor formula, which is 1 over RT is equal to 1 over R1 plus 1 over R2, and so on. Bear in mind, this is definitely a harder question. So they give us the total resistance is 0.25 ohms. And we know that the resistance for each one of those is 2 ohms. So it's going to be 1 over 2. And that's going to be times by the amount of resistors that we use. So if it was 2 resistors, it would be 2 lots of a half. If it was 3 resistors, it would be 3 lots of a half, and so on. So now we have one unknown here. We know what the total resistance is, and we know what the resistor, or the resistance is for each individual resistor. So we can use our algebra skills now to solve this. So if we have 1 over 0.25 is equal to a half times n, well, a half times n will give us n over 2. So when we cross multiply these terms, we end up with 0.25n is equal to 2, and then n is equal to 2 divided by 0.25. So this gives us the number of resistors then that would need to be combined together in parallel would be 8. So there's no unit there because it's just a number of resistors. If you wanted to, you could check that out then again using the 1 over RT formula, just to double check that you've done it right. So the next question we're looking at is question 4. We've got a power supply that's providing 10 volts of potential difference. We've got 2 ammeters and we've got 2 resistors all in series. So we're first of all asked what's the total resistance of the circuit, and because the components are in series, we use our series resistance formula. So RT equals R1 plus R2. First resistor is 200 ohms, the second one is 300. So this gives us a combined resistance of 500 ohms. So the next thing they ask us then is to calculate the current flowing in each of the ammeters. Because the ammeters are in series with each other and there's no parallel branches here, that means that if we can figure out the current for one of these, it's going to be the same as the current to the rest of it, right? For example, if there's 5 amps or 5 coulombs of charge per second flowing through the first ammeter, then that amount of current, or the amount of charge flowing, will be the same through the second ammeter here as well, because it's going to be flowing continuously around in a loop. So there's a few ways of doing this, and the way I think is probably simplest is if we just figure out the current flowing around the total circuit. So use Ohm's law, V equals IR, and for the whole circuit we know that the voltage is 10, we know the current I is, well, we don't know what it is, it's unknown. We know the total resistance for that whole circuit is 500 ohms. So this means the current then will be 10 divided by 500. So this gives us a total resistance, or total current, of 0.02 amps. Alright, and again, if that's the current for the series circuit, then it's going to be the same at any point along that circuit. The only time that would be different is if it's split up into parallel components. So question 5 here is very similar. We've got a circuit that's got 2 parallel branches, and they want us to find first of all the total resistance and then the current through each ammeter. So we'll talk about part A first. So to get the resistance, we know that we're going to use the parallel circuit formula. So the total resistance is going to be equal to 1 over R1 plus 1 over R2. Sorry, I should say 1 over the total resistance is going to equal 1 over R1 plus 1 over R2. So if we fill in our resistance values, then we get 1 over RT is equal to 1 over 50 plus 1 over 100. And simplifying this then, we get 1 over RT is equal to 3 over 100. And then that gives us RT is equal to 100 over 3. Although it's often encouraged in maths to give your answer as a fraction, we want to make sure that we're always given as a decimal in physics. So that's going to be 33. If you're not sure how many decimal places to use, just use 3. So 33.333 ohms. Now the next thing we want us to do is figure out the current in each of those ammeters, A1 and A2. So there's a few ways to approach this. The way I'm going to outline, I think, is probably the most straightforward. So what I'd like to do just to get A1 is I'm going to look at this parallel branch in isolation, right? So this parallel branch just along here. And that's going to make it easiest just to look at the properties of that ammeter A1. So if we look at this branch, we're going to try and apply Ohm's law to figure out that current. Because we know that the resistance of that branch is 50 ohms, and we know the potential difference across it is 20 volts. And we're happy enough to say that it's 20 volts because there's nothing along here that will cause a change in potential difference, and similarly nothing along here. If there was another component here, then that 20 volts might be split up into, say, 5 volts and 15 volts. But we just have one parallel branch here, so we can say that it's 20 volts to get from here to here, or 20 joules of energy per coulomb. So if we use our formula V equals IR, then what we're going to find is that the voltage is 20, the current is unknown, and the resistance is 50. So I then is equal to 20 divided by 50, and we get a current there for that ammeter of 0.4 amps. So we'll say that that's for I1, so we can call, for ammeter 1, so we can call that current 1. For A2, we're going to do something very, very similar. The only difference this time is that it's not part of the parallel branch, so we're just going to treat it as part of the whole circuit, because it's looking at the recombined part. So we're going to get the voltage for the whole circuit, we're going to get the resistance for the whole circuit, and use that to figure out the current for the whole circuit. So again, we'll use Ohm's law formula, V is equal to IR. We know that the voltage across the whole circuit is 20 volts again. The current is unknown, as before. And the resistance across the whole circuit we already figured out is 33.333 ohms. That means the current will be equal to 20 divided by 33.333. So this gives us a current for that circuit of 0.6 amps. Again, I'll just label that as I2 because it's the current from the second ammeter. So next we'll look at question 6. We are provided with a diagram here, so we've got a power pack or something similar. We aren't told what the potential difference is across here, or we could call that EMF because it's a circuit. Again, EMF is just potential difference when applied to a circuit. We're told the current here is 3 amps at this point, but we know that because it's a series circuit, the current is going to be the same at any point along the circuit. And then we're asked to find what the potential difference is across each resistor. So we can call that V1, V2, and V3. In an exam, if you want to just be really clear with the examiner about which is going to be V1, V2, and V3, could be worthwhile doing a quick sketch of the diagram and just labeling it then yourself, so it's very clear which is which. So the way that I would approach this is I'd look at each resistor individually. I know what the resistance is. I know the current through each one is 3 amps. So using Ohm's law, I can then figure out what the potential difference, or the informal term voltage, is across each resistor. So we'll start off with the first one. V is equal to IR is Ohm's law. We're trying to figure out V1. We know that the current is 3 amps and the resistance is 100. So the voltage there is 300 amps or 300 volts. Let's do the same thing for the second one. V2 is equal to IR. The current is 3, the resistance is 50 ohms. So V2 is equal to 150 volts. And we can do the same thing for the third one. V3 is equal to IR. So we have a current of 3 amps again and a resistance of 200 ohms. So V3 is equal to 600 volts. To find the total potential difference then, we can just add each of these individual potential differences up. So for example, if you have to do 300 joules of energy per coulomb to go across the first one, 150 then to get across the next one, so it's additional 150, 600 to get across the third one. And that means that the total potential difference across this circuit is going to be 300 plus 150 plus 600. So VT, our total potential difference, this is for part B. He asks us for the EMF of the circuit. It's going to be 300 plus 150 plus 600. So that gives us a total potential difference, or EMF as they phrase it in the question, of 1050 volts. So now we move on to question 7. You can see we've got a circuit that's made up of a parallel aspect, and then that's connected in series to just another single resistor. So straight away when we see this, we realize we're probably going to have to block this up and treat this as one unit if we're asked to find the total resistance. So the first thing they actually ask us here is to find the total resistance. So like I mentioned, treat this as one block. We can call that or parallel, its total resistance. And then once we find its resistance, we're going to add it to this other component, because effectively or parallel and the 1.2 kilo ohm resistor are in series, so we can just add them. And another thing to be aware of here, I'm spotting it as I'm talking, is that the unit given here for this resistor is kilo ohms. So you have to be very careful to convert that into ohms before we put it into any formula. So if I was doing this in an exam paper, I would be underlining this just to make that very easy for myself to remember. Okay, so if we look at finding over parallel first, normally write the formula 1 over R1 plus 1 over R2. So just make sure you're doing it. And I'm probably skipping some formulae because this video is going to be incredibly long. So let's sub in some of those numbers then. So we're just looking at the parallel component. So it's 1 over 300 plus 1 over 300. That means that 1 over R parallel is equal to 2 over 300. So R parallel is equal to 300 over 2. Or 150 ohms of resistance. Now if we want to get the total resistance of the circuit, we will just treat these like two series components. We've got our 1.2 kilo ohm resistor and we've got our parallel section of the circuit, which are in fact connected in series to each other now. So write the formula again for series components. We've got 1200, which is our 1.2 kilo ohm resistor. We've got 150, which is the resistance of our parallel section. 1200, we got this because kilo means thousand, so we multiply 1.2 by 1000. When we add these, we get a total resistance for the circuit of 1350 ohms. Alright, so for part B, then they ask us to find the total current in the whole circuit, right? So if we look at this whole circuit, we know the voltage across the whole circuit, we know the resistance for the whole circuit, so we can use Ohm's law to find the current. So we'll write out our formula, V equals IR. We'll fill in the potential difference, which we know is 50 volts. our current is unknown, and we know the total resistance is 1350 ohms. Rearrange this, we get the current is equal to 50 over 1350. This gives us a total current of 0.037 amps. Now again, if you're not sure how many decimal places to use, 3 is a good rule of thumb. Part C now asks us what current we would expect to see in the ammeter. So bearing in mind the total current is 0.037 amps, which we figured out from over here earlier on. So that's the total current in the circuit. So we can assume that it's 0.037 amps or 0.037 coulombs per second of charge that are flowing around every point till it gets up to A. Now what's going to happen at A is it's going to split up, and some of it will go through this branch and some of it will go through the other branch. Normally, more current will go through the branch that has less resistance, and less current will go through the branch that has more resistance. However, both of these have exactly identical resistances, so an even amount is going to go through each of those branches. So that means that we're going to take our 0.037 amps and we're going to divide it by 2, and half is going to go into each branch, so half should be going through A. So 0.037 divided by 2 gives us 0.0185 amps of current, and that's what is passing through A, the ammeter. The next thing we're asked for is question D. They want to know how much point potential there is at the point A. So what we take as standard is that the point potential at the positive terminal is whatever the total potential difference of the across the circuit is. So we could say the point potential here is 50 volts. The point potential here is 0 volts. So to find the point potential at A, what we're going to do is just find the potential difference across this component here, our 1.2 kilo ohm resistor. Whatever that potential is, potential difference is, we're just going to take it away from 50, and that'll bring us to where we are at A. So the first step to that, like we said, is going to be to find the potential difference across the 1.2 kilo ohm resistor. Ohm's law, as always, is extremely handy in these type of questions. So V is equal to IR. We're trying to find the voltage. We know that the current in that section is 0.037 amps. And we know that the resistance there is 1.2 kilo ohms. So 1.2 times 10 to the power of 3. Or you could say 1,200. Either one will work. So that gives us a voltage of 44.4 volts. Now that is the potential difference. Again, voltage and potential difference are the same thing. Potential difference is just a more formal term, which would be better to use in the exam. That's the potential difference across this component here. So if the point potential is 50 volts here, the potential difference here is 44.4 volts. Then what we're going to do is just take that away from the 50 volts, and it'll tell us how far we've gotten towards 0. So 50, take away 44.4, gives us 5.6 volts. So that's the point potential at A. So now we're on to our final question, question 8. This one is made up, again it's a circuit. It's got a potential difference of 50 volts. It's got a parallel component, which like always will be served to treat like a single unit. And just try and find the total resistance for that parallel section if we have to find the resistance, which I believe we will straight away. We've got another 9 ohm resistor, and then we've got a third resistor or fourth resistor here of unknown resistance, which is just labeled as X. So part A of question 8 asks us to find the resistance of the resistor marked A. So part A. What I think would be a good idea here is just to figure out the resistance of this section here first. We're going to add then the total resistances together to get the total resistance, or add each individual component together to get the total resistance then. Luckily they tell us what the total resistance is, and that's 25 ohms. So we know that the resistance of R parallel plus the resistance of the 9 ohm resistor plus the unknown resistor should all sum up to 25 ohms. So let's start off with R parallel. Use the formula 1 over R parallel is equal to 1 over R1 plus 1 over R2. So there's two resistors there. 1 over R parallel is equal to 1 over 20 plus 1 over 30. 1 over R parallel, if we try to simplify these without a calculator, we're going to get 3/60 plus 2/60. That's going to give us 1 over R parallel is equal to 5/60. Meaning that the parallel resistance is going to be 60 over 5, which we know from our times tables is 12, and our unit there is ohms. So we know then to find the total resistance, we can use the series resistors formula. So the total resistance is going to be equal to the resistance of the first plus second plus third components. We're going to treat the parallel section as one resistor here. So we write out our formula first. We've been given the total resistance as 25 ohms. Resistance 1 we can call X. Resistor 2, its resistance is 9 ohms. And the third parallel section has a resistance of 12 ohms. So if we simplify this using algebra, we get X plus 21. And that gives us X is equal to 25 minus 21, where X is equal to 4 ohms. So that will give us the resistance of our unknown resistor marked with the X. Next we are asked to find the current that flows through that resistor. So we'll just look at our formula here first and see how much work, or look at the diagram and see how much work we have to do. Luckily this unknown resistor, which we now know has a resistance of 4 ohms, actually is in the series part of the circuit. So if we just figure out the total current for that circuit, well then that current is going to be the same for this component as it would be for the 9 ohm resistor. It would only change when the current has to split up between the 20 ohm and the 30 ohm resistor over the parallel branch, because the amount of charges per second flowing would have to be somehow divided by them. A certain amount of charge would flow through one of those branches, the rest of the charge would flow through the other each second. So let's try then to figure out what that will be. So we can use Ohm's law again. It is the most handy formula to use for these type of questions. It comes up all the time. So again, we're trying to find the total current for the entire circuit. So the total voltage is 50 volts. Total current there is unknown. And the total resistance we're actually given originally is 25 ohms. So this means that the current will be equal to 50 divided by 25. The current there is equal to 2 amps. Again, that current then will be the same the whole way around the circuit, apart from this parallel section where we'll have to split up into two smaller amounts of current. Okay, so for the final part of question 8, we're asked to find the point potential at points A, B and C. The point potential at A we could get fairly easily, because we know the point potential at the positive terminal is 50 volts. The point potential at the negative terminal is 0 volts. And because no work has to be done to move any charge from the positive terminal to A, it doesn't have to go through anything with substantial resistance, we can say the point potential at A is 50 volts also. Point potential would be different if work had to be done to move it to that point. Like for example, you'll have to do work to move it across the resistor X from A to B. So the point potential at B will be different. To figure out what the point potential at B will be, we will just figure out the potential difference across this resistor X here. And we're then going to subtract the potential difference across V1, which we've labeled as V1. And then we'll subtract that from the 50 volt reading that we have for the positive terminal's point potential. And we can then repeat a pretty similar process, and we'll get the potential difference across the 9 ohm resistor. And we will then just subtract that again from the value at B to end up with the point potential at C. So let's start off by just calculating V1, and then we'll find out the point potential at B, then we'll calculate V2, find out from there the point potential at C. So for V1, we can use Ohm's law. It's really handy. Again, you use it all the time, so very high chance you're going to have to use it if you see a question like this. So the potential difference is unknown here, but we know the current is 2 amps. We know the resistance there for X, because we already figured it out, it was 4 ohms. So 2 times 4, V1 is 8 volts potential difference. So if we started off at 50 here, you take away 8, you're going to end up with 42 volts of point potential at B. Alright, so we'll make that nice and clear. Then we'll do the same thing for V2. Ohm's law is going to be used again. V2 equals IR. Current is going to be the same because it's a series component, so it's going to be 2. The resistance there is 9, so V2 is 18 volts. And that's the potential difference across that 9 ohm resistor. So we're going to take 18 away from our 42. That's going to give us our point potential at C. So we get a point potential of 24 volts here. And I'll make that clear there again.